The Doppler effect is defined by the apparent change in the frequency of a wave caused by the relative motion between the source of the wave and the observer. This phenomenon was discovered in the 19th century by the Austrian scientist Christian Doppler.
When a source of the sound and a listener are in motion relative to each other, the frequency of the sound heard by the listener is different from the one of the source.
In front, the waves bunch up, and behind, they spread out. If the object is moving towards a stationary object, the waves have a higher frequency, and if the object is moving away from the stationary observer, they have a lower frequency.
To analyze the Doppler effect for sound, we analyze the relationship between the frequency shift and the velocities of the source and the listener relative to the medium, in this case air, through which the sound waves propagate.
There is also a Doppler effect for electromagnetic waves, where the space is empty, such as light waves and radio waves. In this case, there is no medium that we can use as a reference to measure the velocities. All that matters is the relative velocity of the source and the receiver.
Our objective is to observe the Doppler effect, the frequency shifts, using simple apps as AudioFrag and Sonometer to measure sound intensity in decibels. Using the Sonometer app, record the horn of a car when it is not moving at a speed of 20 km an hour, 40 km an hour, and 60 km an hour, in order to obtain the audio recordings and the graph that compares decibels versus time.
Later import the recordings to AudioFrag to further analyze the frequencies.
The car we used for the subject was a Jeep Wrangler from 2006. To calculate the Doppler effect, we use the formula FL equals V plus VL over V plus VS, all that multiplied by Fs.
Where FL represents the frequency of the listener, Fs the frequency of the source, Vs the speed of the source, VL the speed of the listener, and V the speed of the sound waves. In this experiment, the listener is at rest, so its velocity is equal to 0, and the speed of the sound waves is of 340.
To obtain the frequency of the source, we use the application AudioFrag in order to obtain the hertz. We use different velocities for the speed of the source: 20 km an hour, that is 5.5 meters per second; 40 km an hour, that equals to 11.11 meters per second; and 60 km an hour, that is 16.66 meters per second. When the car is moving towards the subject or the listener, the velocity of the source is negative, and when it is moving away, it is positive.
Results. At 20 kilometers per hour, when the source approached, our frequency was of 409.11 Hertz, and when the source moves away, it was of 396.09 Hertz.
At 40 kilometers an hour, when the source approaches, the frequency is of 416.09 Hertz, and when the source is moving away, the frequency is of 389.76.
At 60 kilometers per hour, when the source approached, the frequency was of 423.23 Hertz, and when the source moves away, it was of 383.69.
Once we introduce the audio recordings into AudioFrag, we obtained that the peak for 20 kilometers an hour was 411.2. For 40 kilometers an hour, it was 416.4, and for 60 kilometers an hour it was 423.8. This is really close to the calculations we had of the frequencies.
The average frequency of the 20 kilometers per hour was of 402.6 hertz, and the difference between the car approach and when it goes away, it was of 13 hertz.
For the 40 kilometers an hour test, we got a frequency average of 402.92 and a difference between approaching and moving away of 26.33.
Finally, at the 60 kilometers per hour, the average frequency was of 403.46 hertz, and the difference between approaching and going away was of 39 hertz.
Once we obtain the frequency average, we can observe that these results are very similar to the frequency of the subject, which was 402.5.
We can observe that the change in frequency was of 13 degrees when it approaches and goes away every 20 kilometers. So we can infer that when we use 80 kilometers per hour, it will be a total of 52 hertz approximately.
As conclusions, we can say that the listener is always going to hear a higher frequency when the car is moving towards him and a lower frequency when the car is moving away. With this, we can test the Doppler effect.
And our recommendation for this project is to record the noise in place with fewer noise interfering with the frequencies that we are recording.